In these related situations, two people are biking around the grounds of a school. We will examine their movement through the use of three frames of reference. First, the observer, sitting and watching them move around. He is in an inertial frame of reference and fixed to the earth, static in relation to his surroundings. Next, in the red sweater, we have Will. Will is traveling at a constant velocity across the schoolyard. We also have Quentin in the navy shirt. We will consider these tests to be occurring within a physics bubble, without the constraints of our bleak and imperfect reality. Human testing conditions make achieving a constant velocity impossible, but for all intents and purposes, Quentin and Will are normally traveling at the same constant velocity. Let's watch the first scenario. As you can see, both bikers move across the screen, by the observer, at the same constant velocities. The frame of reference of the camera is the same as that of the observer, locked to the earth. From this perspective, centering the observer in the frame, both bikers move right across the screen at a constant velocity, making this an inertial frame of reference. However, if we shift our frame of reference to one of the bikers, things look different. Using a camera in the frame of reference of Will's bike, Quentin appears not to be moving, with the world moving around them. Next, let's consider another scenario. First, we'll show an animation of the movement from one of the three frames of reference. Now let's see it in reality. It might not be what you think. Will and Quentin are once again traveling in the same direction with the same velocity. For the first part of this scenario, the properties of the first clip would still apply. However, halfway across, Will quickly brakes and comes to a stop. Quentin continues on as before. By accelerating, or decelerating, the bike's frame of reference becomes non-inertial, and fictitious forces begin to appear. The observer sees what we see, the deceleration of Will to zero velocity. Again, both bikers' frames of reference differ from this. The two start traveling at effectively zero velocity relative to each other, but when Will stops, things change. Keeping Quentin in the center of the frame, it looks as if Will starts to accelerate backwards when he brakes, and then after hitting a top speed, continues to travel back at a constant velocity. For Will, the effect is opposite. Quentin starts at zero velocity, and then appears to start accelerating forwards before hitting a top speed, and then continuing forwards at a constant velocity. Let's take another look at the animation. By isolating the bikers and making the background less identifying, it's harder to tell what's happening. We know what's really happening in the fixed to the earth inertial frame of reference, but here it seems that something causes Quentin to accelerate, a fictitious force. Moving back to reality, we can see another demonstration of fictitious forces in a non-inertial frame of reference by looking inside Will's bike basket. In case of dire emergencies, Will always brings along a glue stick. We will examine its movement during deceleration. Using this top-down view, with clues to the outside inertial frame of reference hidden, we can more clearly see the presence of fictitious forces. When the bike comes to a sudden stop, the glue stick is propelled forward, affected by a force that has no apparent cause. We can use a vector diagram to illustrate this. Not secured to the bike, the glue stick retains its momentum when the bike stops, continuing to move forward before eventually coming to a stop. We can see from these tests that many different frames of reference may disagree in how they perceive motion and forces.